You ever wonder how a massive assembly line just works with perfect timing? Or how a robotic arm knows exactly where to grab something and put it down? Well, I promise you, it's not magic. It's actually a language. And today, we're going to learn the basic grammar, the essential words you need to teach a machine how to think. So, that's the big question, isn't it? How do you take this pile of metal and wires and give it a thought process, a way to react to the world, to make decisions, and to do its job perfectly, thousands of times a day? Well, it all starts by giving it a brain.
And that brain, it has a name. It's the Programmable Logic Controller, or what everyone in the industry just calls a PLC. This little box is the absolute heart of modern automation. It's the main character in our story today.
So what exactly is a PLC? Honestly, the best way to think of it is as a super tough, super specialized computer. You're not going to browse the web on this thing. Its only job, its entire purpose in life, is to run a program that controls a physical process. It reads inputs, like a sensor screaming, "Hey, the part is here," and then it turns outputs on or off based on the instructions we give it. Simple as that. Now, giving our robot a simple step-by-step recipe is easy enough if everything goes perfectly. But, this is the real world we're talking about. Things go wrong, parts are missing. So what happens then? A truly smart machine has to be able to adapt. It needs to make decisions. And this is where things get really interesting. This is where a simple machine starts to get smart. We do it by controlling the flow of its program. Instead of just blindly following a list, 1, 2, 3, we give our robot the power to make choices, to literally jump over steps it doesn't need, or skip entire chunks of its code based on what's happening around it. And here's a perfect everyday example. Let's say our robot is all set to pick up a part, but a sensor tells the PLC, "Whoa, hold on, there's nothing here." We definitely don't want the robot wasting time and energy trying to grab thin air. No way. The program has to be smart enough to say, "Okay, no part, let's skip the whole pickup routine and move on." So, to do that, we have these two really powerful tools, the skip function and the master control relay, or MCR. They both let the program bypass code, but, and this is super important, they do it in very different ways. A skip just ignores the instructions. Whatever was on stays on, whatever was off stays off. But an MCR is like hitting an emergency stop for just one part of the machine. When it's active, it forces every single output in its zone to the off state. It's a failsafe. You'd use a skip for a simple process change, but you use an MCR when you need to guarantee that a part of the system is safely shut down. Okay, skipping stuff is great, but what if you have a task you need to do all the time? Like, say, flashing an alarm light or running a very specific delay. You really don't want to write that same code over and over and over again. It's messy and inefficient. And that's where we use this really clever trick called a subroutine. Think of it like putting a bookmark in a book. The main program is just chugging along, doing its thing, and then bam, it hits a jump to subroutine command. The program literally leaps over to this separate mini program. It runs that code, maybe it flashes an alarm light for 5 seconds, and when it's finished, the return command sends it right back to that bookmark to pick up exactly where it left off. It's incredibly efficient because you only have to write that alarm code one time, and you can call on it from anywhere. All right, so a robot can follow a sequence, and it can make decisions. That's pretty good. But to be really useful, it also needs to handle information. It needs a memory to keep track of all the data that's driving the whole process. I mean, think about it. How long should this timer run? What's the exact position of the arm right now? What's the value coming in from that sensor? All of this is critical data, and the PLC needs a way to store it and, more importantly, to shuffle it around to where it's needed. And the main tool for that job is the beautifully simple move function. It does exactly what it says on the tin. It takes a piece of data from a source, a little memory slot called a register, and it copies it over to a destination register. It is literally the PLC's version of copy and paste. But there's a really, really important catch to how this whole copy and paste thing works. And it's one of the first things you learn, because if you forget it, you can accidentally wreck your own program. And here it is. The original data, the source, it stays right where it is, totally unchanged. But whatever was in the destination location before you did the move, it's gone. Poof, completely overwritten. So the rule is simple but critical. If you need that old data, you better save a copy of it somewhere else first. So we can control the program's flow, we can manage its data. Now let's put it all together. How do we orchestrate a really long, complex series of actions where tons of things need to happen at each step? For that, my friends, we use the undisputed king of automation functions, the sequencer. You know, the whole idea actually comes from these old school mechanical controllers. Literally a big metal drum that would spin, and it had little pegs on it that would physically push switches to turn things on and off in order. The PLC sequencer is just the incredibly powerful digital version of that. It's basically a big grid, a matrix of steps and outputs. You want a perfect example you use every day? Your dishwasher. Just look at this table. Each row is a step in the cycle, right? And each column is a part of the machine. So for step 1, fill, the water valve is on and everything else is off. Easy. Then for step 2, wash, the soap valve and the wash motor turn on. The sequencer just marches down this list, step by step, turning the right things on and off at the right time. It's such a clean, organized way to program a complicated process. And now we can apply that exact logic right back to our robot. Each of these 9 steps would just be a row in our sequencer's matrix. And at each step, the PLC just turns on the right motors and valves to make the move happen perfectly. The sequencer makes choreographing this whole robotic dance incredibly straightforward. Okay, we've looked at the individual tools in our toolbox. Now let's just zoom out for a second and see how these simple little pieces can combine to build something massive.
When you really get down to it, it all boils down to these 3 things. You need to control the flow of the program. That's what makes it smart. You need to handle data. That's what gives it a memory. And you need to sequence the actions. That's what gives it the master plan to follow.
And this is the truly amazing part. The very same logic we just talked about for one simple robot, the jumps, the moves, the sequencers, those are the exact same principles used to automate an entire car factory or a massive bottling plant. The scale gets bigger, sure, but the fundamental building blocks, they're exactly the same. And that's really the big idea here. Once you get these core concepts, you're not just programming one little machine, you're learning the language of automation itself, which kind of makes you wonder, if these are the simple Legos, what's the most complex thing you could possibly build? What's the most incredible machine you can imagine bringing to life?